Hello everyone. I'm Ray Miyazaki from the Institute for Catalysis, Hokkaido University, Japan. First, it is my great honor to join this very nice FHI tutorial. Then I'd like to thank for Konstantin and the other people of the MS1P and the FHI. Today, I'd like to talk about the density functional theory approaches for modeling heterogeneous catalysis. Before entering my talk, I would like to briefly introduce myself. My name is Ray Miyazaki. Currently, I'm an assistant professor at the Institute for Catalysis, Hokkaido University. Actually, I got a PhD in the same laboratory with Professor Junya Hasegawa. And then I did a 1-year postdoc, and then from 2021, I moved to the Fritz Haber Institute of the Max Planck Society as a postdoc. And at that time, I worked with Dr. Lucas Fopper and Professor Matthias Schäfer. And then from 2023, I moved back to Japan and then became an assistant professor. So now I belong to the Hasegawa group. So now we have the 10 members. Actually, it is relatively small group, but I believe that we are a very active group. This is a brief introduction of our institute. So here, this is a map of the Japan, and here's the Tokyo and the Kyoto in the main island. But our institute located in here, Sapporo City, so located in the northern island of the Japan. So the Institute for Catalysis has the 9 research divisions with 25 faculties. And actually, our institute is relatively small, but they have the long history. Actually, our institute was established in 1943, and this is the oldest research institute named after the catalyst. And also, there's a historical long friendship with our institute and the Fritz Haber Institute. Because our institute located in the northern part, in the winter, we have a lot of snows. Actually, I took those photos by myself in our university in midwinter. And nowadays, of course, the amount of the snow at the road is decreased and decreased, but still we are in winter. But soon, probably several weeks after, we will have a nice spring season. Then I say Hokkaido is a very nice place and our institute is very nice. This is a very brief introduction of myself and the institute. So let me start the scientific part. So first, I would like to talk about my scientific interest. So this is a very typical equation of the chemical reaction. Here, A plus B generates a C molecule. And if you add the catalysis and with temperature and pressure, we can control the, the product of the C or ratio of the C. And this reaction connected by this arrow. But point is, in the textbook, there's a very limited description about the mechanism behind of this arrow. So then my interest is what is happening behind these chemical reactions during this arrow. So then my research purpose is proposing the reaction mechanisms and design criteria for new catalysts by theoretical calculation and recently AI. So for example, by using ab initio calculations with like a DFT, we can get this kind of reaction pathways of the catalytic reactions. And then from this, we can extract some kind of catalytic mechanisms. Or we can use experimental and or theoretical data, and then we can combine those data by using artificial intelligence, and then we can get some kind of descriptive parameters that correlate with the target catalytic performance. And then by using those approaches, we can get a design criteria for new and high performance catalysts. And this is my, the main research topics recent days. And the target is heterogeneous catalyst. And most of you already know the heterogeneous catalyst is very essential and important technology or materials for the modern society. For example, this can generate the useful chemical compound from raw materials. And then we would like to develop a new and high performance catalyst. But the problem is the heterogeneous catalyst itself has very highly complicated structure. And that means there's a lot of factors that affect the catalytic activity. Here, this is a very typical picture of the heterogeneous catalyst. Here is a metal nanoparticle supported on the support material. And for example, here, metal, of course, metal surface is the active site, but also interfacial site between the metal and the support material is a very important active site also. And this metal nanoparticle itself also has a very complicated structure, like several facets and several active sites. Then, due to this complexity, what kind of reactions takes place where in the catalyst is a very big question for us. And of course, the mechanism of catalytic reaction that proceed in the atomic scale is hard to be elucidated only by experimental approaches. Then, electronic structure calculations. So because by using these electronic structure calculations, we can get atomic scale reaction pathways and effect of electric state of the catalyst to the mechanism. Then it is very nice approaches, but problem is due to this complexity, it is very hard to explicitly include all of the structures and factors of the catalyst to the atomistic model with ab initio calculations. Then we need to extract the factors that essentially contribute to the catalysis that enable us to the elucidating the underlying mechanism and principles of the catalysis. And also I was to stress that we need a collaboration with the experimental groups because by using both both sides of the narratives from theory and experiment, we can propose the design criteria for the new catalyst from both sides. So this is a very general introduction of the heterogeneous catalysis with electric structure calculation. So today I would like to focus on the one application of my DFT calculations for this CO2 hydrogenation by cobalt catalyst, and most of the results are published in those two papers. So, and in this project, I focused on this cobalt catalyst. Here, cobalt nanoparticle is supported on the modified amorphous silica support. And the important point is some kind of these additive metals are incorporated in the silica support. And in this kind of catalyst, not only this metal nanoparticle, but also the support material and the interaction with them are very important for the catalytic performance. Then the difference of the support material is very important for catalytic activity. But the design criteria for the optimal support materials are not fully established yet. Then in this study, we particularly focus on the role of the modified silica support for the CO2 hydrogenation by using this catalyst. And this catalytic system is quite unique because our collaborators, mimic the hydrothermal vent environment by using this catalytic system. Hydrothermal vent is the fissure on the seafloor and then discharging some hot water from the seafloor. And this related to some kind of origin of rise. And then our collaborators investigated how first organic molecules are generated at the hydrothermal vent by using this catalytic system. And this is a computational details for my research. And of course, all of the calculation performed with the FHI-aims. And even though, the version of the FHI-aims is a little bit older, but it was very nice. And I performed all of the calculation in DFT level and with RPB functional. And because the ground state of the cobalt is a ferromagnetic state, then I adapted the spin collinear calculation for simulation. And for geometry optimization, I adapted the right basis set. Then by using the optimized structure, I performed a single point calculation with tight basis set to get a reliable or more accurate electronic structure and the analysis. So then we would like to perform some kind of DFT calculation for this catalytic system, but then we need to build the theoretical models of the target system to perform this. But there are difficulties to achieve this. For example, this is a target catalytic system. For example, for this metal cobalt nanoparticle, the experimental particle size of the cobalt is about 8 nanometer. That means it is super large for DFT calculations. Then we cannot be handled directly with DFT, this size of the metal nanoparticle. And for support material, the support material has the amorphous structure. Then one question is how to model this kind of non-crystalline amorphous surface with DFT. And the final one is there are incorporated metals into the silica, but how to incorporate those additive metals structures, what is the structure or what is the electronic structure of them. Then, and also, since the experimental information is limited, detailed structure like shape or morphology is unknown for this kind of heterogeneous catalyst. Then, explicit atomistic modeling with DFT is rather challenging. Then, practically, we need to focus on the physical-chemical properties of the catalyst that would correlate with the performance. For example, first, this cobalt nanoparticle part, again, this is a super large for DFT. Then I adapted this cobalt 20 cluster model. And actually, cobalt 20 cluster here is about 0.5 nanometer. That means this is super small than the actual particle size in experiment. But this is a very, how to say, practical size for simulation. But fortunately, there's one previous study. Based on that study, from around the cobalt 55 size, the adsorption energy of the small molecules is almost constant against the size of the cobalt cluster. That means this cobalt 55 is a lower limit for simulating the cobalt nanoparticle with small molecule. Then the result with cobalt 20 model can be compared with those of the cobalt 55. Then if result is qualitative or quantitatively similar or same, that means the cobalt 20 cluster model is one of the, how to say, the reliable model for the simulation. And for silica, this is also fortunately, the amorphous silica surface model was already built by using MD, molecular dynamics, and DFT calculations by Thomas Bibbs. And then in this study, they performed the molecular dynamics simulation with high temperature, and then making non-crystalline structure, and then gradually cooling down the simulation, and then finally gets this kind of amorphous silica structure. Then I picked up this model from this literature and then performed the geometry optimization with our computational setting, that is FHI-aims with RPB function. So then now we have the two models, that is the silica surface and the cobalt cluster. But next question is how to put this cobalt 20 cluster onto the amorphous silica surface slab. Because as I mentioned, this is the amorphous surface, then that means there's no symmetry of the surface. Then we can freely put the cobalt cluster onto it. Then based on this previous study, this kind of metal nanoparticle contact with the silica by removing the hydrogen from OH group. That means by contacting the metal nanoparticle, this metal nanoparticle directly bonded with the silica via oxygen atom. Then, as you can see here, I counted up the OH group on the surface of this model, and there are 32 OH groups. Then I put the cobalt 20 cluster model right above each OH group, and then removing the hydrogen atom that directly contact with the cobalt nanoparticle. And then I performed the geometry optimization on each point and comparing the relative stability of them. And this is the result. And I actually calculated the formation energy of this cobalt 20 with silica slab. And this is just means the negative energy with this energy, this equation means the stable structure. Then here y-axis represents this formation energy, and the x-axis represents the index of the structure. Then I perform the geometrical optimization of each point, and then I finally got the most stable one, this one, number 23. And this structure shows the minus 2.2 to 4 electron volts for formation energy. And then that means this is very enough stable for this contacting the cobalt cluster and the silica slab. And this is obtained most stable one. This is the top view, and this is the side view. And here, cobalt nanoparticle, cobalt cluster model is contact with the silica with 5 OH group without hydrogen. And the next question is, okay, now we can get this kind of theoretical model for cobalt catalyst, and then what we can do. So first, we can, of course, investigate the electronic structure. Here, I investigate the atomic charge of each cobalt atom. And then by using high-field charge analysis, we can get this atomic charge. And then in FHI-aims, you can use this kind of keyword in control.a file. And here I show the result of the hash-field charge analysis, and then I picked up the top 3 negatively charged cobalt atoms and the top 3 positively charged cobalt atoms here. And this is the blue one is a negative one, and the green one is a positive one. And as you can see here, most of the positively charged cobalt atoms are located at the interfacial site with the silica, but the negatively or neutrally charged cobalt is located at the top layer of the cobalt cluster. Then that means the interfacial the cobalt at the interfacial site has the positive charge or cationic cobalt due to the interaction with the silica sample. Then we can get such kind of electronic structure information from those kind of calculation. And then next, of course, because we are interested in the catalysis, that is CO2 hydrogenation, then we are interested in the interaction with molecules and the catalyst. And here I investigated the interaction with CO2 and this cobalt cluster model. And I calculated the adsorption energy of the CO2 here. This is the energy of the total model, and the isolated energy of the isolated model is subtracted. And here, because as you can see here, there's a lot of adsorption sites of the cobalt cluster. Then the question is how to put or where should we put the CO2 molecule on this model. And then I picked up the most negatively charged site and most positively charged site of the cobalt cluster. Because as I showed before, we know there's some different charge balance inside of the cobalt cluster. Then I'm interested in this difference. So here, this is a CO2 adsorption structure as the most negatively charged, or that means metallic cobalt site. And the actually calculated adsorption energy is minus 0.5 electron volt. But for the cationic site at the interfacial site, adsorption energy calculated to be the minus 0.27 electron volt. That means the CO2 prefer to be adsorbed at the metallic cobalt site here. And then this interfacial site is not the most stable or preferable CO2 adsorption site. And as I mentioned, cobalt-20 cluster is too small for actual compared with the actual cobalt cluster. Then we need to assessment of the reliability of this cobalt-20 cluster. Then, as I mentioned before, this can be done with cobalt-55 based on the previous study. And I also constructed this cobalt-55 SiO2 model with this cobalt-55 cluster. And I put the CO2 at the most negative side and the most positive side again for cobalt-55. And as you can see here, the CO2 adsorption energy for metallic cobalt site is more stable than interfacial site. That means this trend is same with the cobalt-20 cluster model. Then, the adsorption trend of CO2 is qualitatively, not quantitatively, but qualitatively represented by cobalt-20 cluster model. Then, even though cobalt-20 cluster model is smaller than the experimental particle size, but that model has some kind of reliability for the simulation of the small molecular interaction with cobalt nanoparticle, with DFT. So, and then now we can get some theoretical model of cobalt cluster onto the amorphous silica. And then the remaining question is, how to incorporate the additive metal to represent the difference of the support material. But the problem is we only know the experimental metal silicon ratio. That means the actual structures are unknown. Then we need to focus on the specific point of the catalyst. Now we are interested in the interaction between cobalt and additive metals at the interfaces. Then I decided to focus on the additive metals in the stable oxidation state at the interface site. So this is what I mean. So actually I incorporated those additive metals with keeping the stable oxidation state of each metal. For example, here this original silicon and the titanium or zirconium generally prefer to be the 4+ oxidation state. But then I simply replace the silicon atom by titanium or zirconium. Then this additive metal site interact with the 4 oxygen atom. That means this additive metal has the formerly 4+ oxidation state. But for aluminum prefer to be a 3+ state. Then once I replace the silicon atom simply by aluminum, the charge balance is unstable. Then we need to keep a system to be neutral. Then we need to put the 1 proton as the oxygen atom surrounding the aluminum site. And then in this model, I put the aluminum and also proton at the interface site. And for finally, calcium and magnesium, those metals prefer to be 2+ state. Then I put those metals at the bridge site between 2 OH groups by removing the 2 hydrogen atom like this. And then this metal interact with the 2 oxygen. That means this metal to be formerly 2+ oxidation state. Then of course, there's a lot of possibility for the actual or operanto structure of the additive metals into the silica support, but I put the one assumption, probably those metals prefer to be a stable oxidation state itself. Then remaining question is, where should we incorporate the additive metals onto the silica support? And again, this cobalt-20 cluster is directly interact with the 4 SiO4 units. Then at the interface site, then I simply replace those silicon atoms by titanium and zirconium, and then compare the stability. Here, this is a result. And actually, I replaced the A, B, C, D silicon by titanium and zirconium, and then calculated the relative stability. And then based on this calculation, replacing this D site is the most stable one for titanium and zirconium. And a similar strategy adapted for aluminum and calcium and magnesium. And then we can decide where should we put these additive metals onto the silica. And yes, and by using those obtained cobalt-20 MSiO2 model, we can investigate the difference or effect of the difference of the support material. For example, this is a result of the CO2 adsorption at the interface side of each model, titanium, zirconium, aluminum, or something. And then here is the calculated adsorption energy. And as you can see here, the obtained adsorption energy of the CO2 at the interface site is actually quite different depending on the additive metal. That means even though I just put the one additive metal, this is quite far from the experimental silicon metal ratio, but this very simplistic model can represent the difference of the support material for CO2 adsorption. And we can also extend to the reaction mechanism. And this is a brief reaction mechanism of the CO2 hydrogenation. This is a very brief one, but as you can see here, the CO2 hydrogenation is very complicated. But there's 3 main reaction pathway was proposed by this paper. The COOH generation pathway, CO generation pathway, formate generation pathway. These are those 3 intermediates recognized as the very important initial 3 reaction intermediate for CO2 hydrogenation. And for methanol formation, this methoxy intermediate recognized as the final intermediate. And then I picked up those 4 key intermediate, and then I investigated the adsorption energy or relative stability of those key intermediate onto each cobalt model. And like this, I put the formate, CO8, CO, and methoxy at the interfacial site of each model, and they calculated the relative stability. Here, this is a result with different additive metal. And as you can see here, the relative stability of each intermediate is quite different depending on the type of additive metal. Then that means the preferable reaction pathway of each additive metal would be different. That is very important result. And of course, by using those information, we can further extend to the reaction mechanism investigation. For example, we can calculate the transition state, the connecting each intermediate, what I showed before. And then finally, we can get energy diagram here. This is a y-axis represents the energy, and the x-axis represents the reaction coordinate. And then we can get the reaction pathways. And by comparing those pathways, we can get main reaction pathway towards the target product. And this kind of calculation can be achieved by using naturally elastic band calculations with atomic simulation environment and FHI-aims. And or you can get some more detailed electron structure analysis here, even though this is a different catalytic system, but performed with FHI-aims. For example, this is a charge transfer from support material to the supported gold cluster, and you can get some reason or mechanism for the high activity of the catalyst by using this kind of analysis. And this analysis can be achieved charge density difference analysis by using output cube total density in control.in file of the FHI-aims. And then by using those kind of information, we can get some design criteria for new catalyst. And even though, sorry, actually, those kind of investigation was not performed with the cobalt catalyst, but those calculations actually performed in this paper. Then if you are interested in, please check this paper. And this is actually my approaches for heterogeneous catalysis with DFT. And actually, as you can see here, DFT calculation is very powerful for investigating atomic scale process, that is the atomic chemical reaction that surface is very powerful for DFT. But actual, heterogeneous catalysis is interplay of between the multi-scale processes. For example, transportation of the reactant product gases at the experimental reactor. This is a macro scale, or reconstruction of the catalytic material under the reality experimental condition. This is a meso or micro scale process. Then, it is very difficult explicitly modeling of the full catalytic progression by using DFT calculation. But of course, atomic scale information hard to be obtained from experiment. Then another idea or another application is, of DFT is we can integrate DFT data with experimental data by using AI. But the time is limited, and also, today's main focus is the DFT. And Constantine mentioned that the upcoming FHI webinars and other speakers will focus on the AI application with FHI-aims. Then I will not detail talk about this, but we can achieve this. And for example, we can get we can combining experimental data and the DFT data with AI, and then we can get this kind of descriptive parameters of the target catalytic performance. And also, this AI is obtained by this approach developed in the FHI, and we can get some analytical expression for the target catalytic performance. And this descriptor contains both experimental data and the theoretical data, and we can get some very good starting point for investigating the further catalytic mechanism behind the reaction. And for this, of course, DFT calculation is very useful to extract some information. And also, of course, we can screen the candidate materials with high performance by using more, how to say, the AI model with low acquisition cost data, and then we can quickly screening the or predict the catalytic performance of the candidate materials and then propose the new material for experimental group. Sorry, the final part is very quick, but I hope the upcoming FHI webinar will focus on the more detail about the AI approach for the heterogeneous catalysis. But my conclusion is, of course, DFT calculations with FHI-aims are very useful for simulating the heterogeneous catalysis. But unfortunately, heterogeneous catalysts have complicated structures, and thus we need to focus or extract the important part of the catalyst. And as I showed, by using the DFT calculations, we can access the underlying mechanism of the catalyst, and those insights can be combined with AI. And the more details are summarized in those papers. And finally, I'd like to thank for my collaborators, and the Professor Matthias Schiffer and the Dr. Lucas Foppa at the Fritz Haber Institute and the Nomad Group. And the experimental collaborator is Harun and Kendra at the Max Planck Institute for Core Function. And I would also thank for the funding from the Big Max and the FunCat project. And thank you very much for your kind attention.
Thank you, Ray. Very nice talk. Thank you for staying on time. So this was all perfect. So I think we can continue with the Q&A part. So I will hand over again to Andre to handle the questions. Feel free again, write in the Q&A chat box. You can also write on YouTube if you're watching there, and we'll see it as well as on Kusha. So I'll hand over here, Andre, please go ahead.
Thank you, Ray, for a very nice presentation. So if you have any questions, please feel free to write. Okay, we'll give some time to type in the questions, or you can raise the hand and we can let you speak if that's more convenient to you. Okay, there is one question from Ashok Kumar. Does FHI-aims support on-the-fly pseudopotential generation for such complex heterogeneous catalysis calculations?
Actually, is it better to answer by myself, or should I ask Volker? But in my understanding, first of all, FHI-aims do not use a pseudo potential. Probably he would like to talk about the machine learning potential, like implemented in BASP, like. I'm not sure, but in my understanding, there's no implementation, right, Volker?
Yeah, no. So in parts, that's because FHI-aims is actually efficient with the all-electron implementation. I think that's a relatively frequent question. So what we're trying to avoid is to actually have to parameterize pseudopotentials, because we can do the calculations with the method that does not need to change the underlying potential with various problems that could arise. Now, that being said, so pseudopotentials come up as a frequently asked question, and so it is on the list that we've sort of formulated for ourselves to add in optional pseudopotentials for some things if we can. Where pseudopotentials certainly exist, and that's relevant for catalysis, is as embedding pseudopotentials, so electron-free pseudopotentials in the context of embedded cluster methods, for example. So ChemShell from Cardiff that was mentioned on one of the slides, one of these methods, and that's definitely something where they've been used for a long time in FHI-aims. We do have a frozen core approach implemented in FHI-aims that also reduces the computational effort, especially for large systems. If you're interested in just working with a set of valence semi-core electrons, and that's also documented.
Thank
So
you very much
maybe
for the
I can add actually, because I mean Ray already said it could be that the question was a little bit misspelled, because on the fly sounds a little bit like machine learned potentials. So what we have already, but not public, but it will be public in a month or so, is on the fly machine learned potentials for geometry optimization, and we are working on it. So probably there will be a webinar in August where we will have all the machine learning aspects which Ray has mentioned, including really machine learned potentials. And I should also say, maybe later Konstantin will say that anyhow, we will have an in-person meeting in November in Shanghai, where we also have a full session on artificial intelligence, including CISO and machine learned potentials and deep H. So that exists already, but it's not public. So there is a beta version which you can get, but otherwise, if you wait for 2 months, and it will be really public as part of the GIMS, of the graphical user interface.
Thanks a lot.
Sounds very exciting.
Yeah. There's also one question from Hashitl to Ray. What criteria did you use to select the orientation of the nanoparticle to be absorbed on a substrate?
Okay, yeah, that's a very good question. So, yeah, actually, I skipped at this part. So, actually, I picked up the most planar, how to say, the side of the metal cluster, and actually, that is the reason why I know the metal cluster is interaction between the metal cluster and the support material is stabilized by interaction with oxygen atom. Then I'd like to, how to say, maximizing this interaction with metal nanocluster and the support material. And then I picked up the most planar and the most large facet of the orientation of the cluster when it interacts with the silica slab. And then I picked up this most planar site. I hope this is the answer for this.
Thanks a lot. There is one more question from anonymous attendee. How do you consider the magnetic behavior before making a slab?
Okay, good question. So actually for silica, there's a no magnetic, no complicated magnetic structure, I believe. So this is a singlet state. But for cobalt cluster, yeah, actually I picked up the, this cobalt cluster structure from the previous report. And actually that previous report also investigated those two papers, investigated the magnetic structure of the cobalt cluster. And then actually even for the bulk cobalt, the ground state is a ferromagnetic state. Then I put the triplet state of each cobalt atom as the initial spin state for geometry optimization. And then after the SCF calculation and geometry optimization, of course, the optimized electron structure is slightly deviate from the original triplet state, but keep the ferromagnetic state. And it is actually stable than the singlet state. And another point is, as I mentioned, actually in my another study, this is a gold nanocluster is supported on the manganese oxide. For manganese oxide, we needed to think about the spin structure. In this case, in experiments, the anti-ferromagnetic structure is reported as the most stable one, and then I put the anti-ferromagnetic structure as the initial spin state for geometry optimization or SCF, and then actually after the SCF we can get the stable anti-ferromagnetic structure. Then you are right, actually before performing the calculation we need to know or investigate the most stable spin or magnetic structure of each material. Yes.
Thanks a lot. Hope this answers the question. Yeah, there is one more question from Oscar van Vuren. Have you considered the possibility of cationic defect species from the silica migrating into the cobalt nanoparticle? Is this something that your experimental collaborators could probe?
Actually, that is also a very nice question. So, yeah, that is unknown. Even now, it is very unknown part for me. So, actually, my experimental collaborator mentioned that for a particularly for titanium case, they investigate this kind of, how to say, distribution of the titanium region at the silica support. And then they found that, for example, for zirconium or aluminum, those species are, how to say, randomly dispersed at the silica. That means the, atomically dispersion. But for titanium, they found that, of course, there's some kind of atomic site of the titanium, but they also found the kind of island structure of the titanium oxide at the interface. That means as you know, the titanium oxide probably making some kind of cationic or charged defect of the oxygen. Then that would also contribute to the high catalytic activity, I think. But as I mentioned, it is unknown things for me because this is actually experimental information, but the very complicated thing, then we need to carefully investigate this. And actually, in this study, we would like to make some data for AI, and then this kind of special data for titanium is not so good for AI because those kind of data or information are lacked for zirconium or other metals. Then I have not carefully focused on this part, but in particular at the operant situation, probably this kind of oxygen defect formation and, for example, stabilizing the metoxic species at the defect would be possibly happened. But that is, we need more how to carefully modeling this, and also experimental, based on the experimental metal ratio at the surface, we need to put at least 10 titanium atoms on the surface. But in this model, I only put 1 titanium atoms, as I mentioned in my talk. Then this is a approximated model for the catalytic system. But if you are interested in this kind of oxygen defect, we need to make a more realistic model for catalysis.
Thanks a lot. There is a next question from Xiaoqing Liu from Kushare, and the same question was asked by James Misaka. How do you perform basis set superposition error in FHI-aims for catalysis, particularly for absorption energy?
Yeah, good question. Actually, for this calculation, I haven't adapted any BSSE correction. But in my understanding, recently it was implemented in the FHIs, right?
I can comment.
Yes.
So I think this is a frequent question from the quantum chemistry community, but it's also actually one of the strengths of the NAO basis sets for DFT, that we don't need a BSSE correction in practice. So this is already addressed in the first FHI-aims paper in 2009, and that experience has not changed. So the DFT BSSE errors that are reported elsewhere, I think they often arise near the nucleus, and our NAO basis functions near the nucleus actually are very good and very precise. So the BSSE we have is very small, and so we carried out tests initially, and those tests indicate that our basis set error is not even close to primarily BSSE. In fact, if you want to increase the basis set, you may improve other things of the density, but the BSSE is not the biggest problem. And so we don't need a BSSE correction for density functional theory calculations typically. And for correlated methods, this is different because you have a sum over unoccupied states, and there we can do a BSSE correction. And I think that's what Ray is also referring to, that there's a recent discussion about BSSE correction and how to do that for periodic systems in the right way for a random phase approximation. But for the calculations here, it actually isn't a strong necessity. So they work without all over FHI-aims.
Thank you, Volker.
Thanks, Volker. I hope this answered the question. There are several more questions. So one question is from anonymous attendee. What are your thoughts on using Bada charge instead of threshold charge?
Okay, so that is also a good question. So actually, first of all, when I performing this calculation with FHI-aims, there's no implementation for generating the appropriate charge density for performing the beta charge analysis. Then I picked up the hash field charge analysis implemented in FHI-aims. But after that, formation generating the electric density for beta charge analysis was nicely implemented in the FHI-aims. Then now we can perform the beta charge analysis with FHI-aims. But important point is there's no golden standard for charge analysis because that is very, how to say, artificial analysis. Then because we have to decide where is the electron located, but in real, electron is moving around. Then my opinion is, okay, even with hash rate analysis or beta charge analysis, we need to be checked with those results with different aspect. For example, this charge density difference. Charge density difference is just how to say, kind of raw data of the electron structure. And then this is just a difference between the interacted system and the isolated system. And then here, as you can see here, yellow region is the electron accumulation region, and the blue area represents the electron depression region. That means here the charge transfer from support material to cluster is nicely represented. And also in this system, I performed also a hash field charge analysis, and the hash field charge analysis also shows the charge accumulation at the cobalt cluster. Gold cluster. That means that those two results are in good agreement with each other. That means the charge density, population analysis is very nicely worked for this system. Probably kind of similar result would be obtained even with beta or NPA or Barrican charge analysis. But the important point is we need, in my opinion, we need to check the electric structure with different aspects, like those charge density difference or population analysis. This is my opinion.
Thanks a lot, Ray. And there are two more questions by Masood. How do you find the morphology and the size of the supported cluster?
Okay, thank you. And I actually, sorry, I completely forgot about the mentioning about the, thank for the previous study. And actually, in those two studies, they are investigated the stable structure of each size of the cobalt cluster by using global optimization method. And then probably in this reference number 1, they investigated the several size of the cobalt cluster, and then actually I picked up the cobalt 20 cluster because this is a I would say for me at that time upper limit for performing the DFT calculation for simulating the catalysis for my environment, and then I picked up this one. But then I haven't myself haven't performed any global optimization, but thanks for these previous studies, I can pick up the stable cobalt cluster in the gas phase. Of course, I don't know the stable structure of the interact with the silicon and cobalt, but we need to pick up this kind of stable cluster at the gas phase as the initial structure for geometry optimization.
Thank you. One more question from anonymous attendee. Have you taken the van der Waals forces into account in your calculations? So these forces can significantly influence the properties of molecules, especially in systems where intermolecular interactions are important. It's essentially to include them for accurate results. Yeah.
Yeah, right. So actually, in this calculation, I just use the simple RPBE without any van der Waals correction. But before performing this calculation, I have checked the accuracy of RPBE and RPBE with van der Waals correction. For this, I adopted Takechenko-Scheffler type van der Waals correction, van der Waals correction. And actually, I investigated the CO, adsorption energy of the carbon monoxide on the cobalt surface, because there is some experimental report for the adsorption energy and the vibrational frequency of the CO on the surface. And then I realized that, as other people mentioned, van der Waals interaction is very nicely for represent the adsorption of the, how to say, physics of the molecule on the metal surface. But if we directly use not without correction, the van der Waals correction for chemi-solved structure, actually adsorption energy of the small molecule is largely overestimated. And even actually, indeed, for the carbon monoxide adsorption on the cobalt surface, adsorption energy of the DFT are largely how to say, deviated from the experimental result if I put the van der Waals correction. Then I decided to not use the van der Waals correction for this calculation. And of course, I also investigated the crystal, lattice constant of the bulk cobalt with RPB, and then, yeah, those are also well represented. And vibration frequencies of the CO molecule on the cobalt surface is also nicely represented by bare RPB. Then I decided not to use the van der Waals correction for this.
Okay.
Maybe I can add a little bit to that. So what we find in general is that the Tkachenko-Scheffler, which was the very first development, right, is somewhat overestimating van der Waals corrections. And if you come to short distances, PBE in fact has some van der Waals included, obviously already. So in general, if you want to include van der Waals, I think one should also go beyond Tkachenko-Scheffler, but one should really go to the many-body dispersion to have a more realistic thing. But again, for short distances, if you really look at chemisorption, that is not so important for these systems. For other systems, if you would have layered compound or something, of course, then you should include many-body dispersion. But the Tkachenko-Scheffler is giving you an idea, but I would say you should really go to the next generation.
Okay, thank you very much.
Thanks, Matthias. Unfortunately, we are short on time, so let's do one last question, I guess. Dr. Tsutagema asks, are the energies in your results compared with experimental results? If yes, how are the single point DFT energies corrected for better comparison with experimental data?
Actually, that's a very difficult question, I would say. Ideally, we should compare our result with experimental data. And for some systems, we can do that. But for heterogeneous catalysis, it is very difficult to get a reliable experimental result that can be compared with the DFT data. Even for adsorption energies, it is very difficult to get them. And actually, I have asked our collaborator to get some kind of data, but it's a bit difficult. But I would say, actually, as I mentioned in the previous Q&A session, I found some kind of experimental data for carbon monoxide adsorption of the cobalt surface. This is the, surface science topics. But it can be compared with DFT. And then, as I mentioned, RPB functional is qualitatively represents the experimental result. Then, RPB is not so bad selection for this simulation, I would say.